Hi there. Today we're looking at chip placement with deep reinforcement learning by Azalia Mirazaini, Anna Goldie, and a long list of authors that I have no stamina to read down. I'm sorry. So this work is a cool application of reinforcement learning to the real world. And we're going to go through it, and the cool thing about it is it pulls together parts from so many different areas of machine learning and also here chip engineering. So what's the fundamental problem? The fundamental problem of chip design is this. You have a canvas, an empty chip, and you want to build a computer chip. Now what you have given is a so-called netlist. So your netlist is any parts that you want on that computer chip and their shape or their size. So you can imagine this like a bit of a Tetris game. So here's this netlist. There's this part and then this part, and then there's maybe this part and also this part. Many parts. Now these, as I understand it, can be thousands of parts, but you can sort of group them together. But still, there are a lot of these parts. And the netlist also contains information about how they're connected. So for each of these parts, you would have a list of which other ones of these parts they must be connected to, right? So maybe it says, okay, this part here needs to be connected to those three parts. And for each of those, you'd also have like a list of how they must be connected. You can represent this as an adjacency matrix, right? But ultimately, this is a graph of these nodes. Now, your goal is to place those things on this board. So for example, we're going to place this right here, and we're going to place the second one maybe here, and the third one maybe here. So you can imagine if this is a CPU, maybe, look, I have no clue of chip design, but imagine it like this. This is your clock that you need on there. This is your NAND gates, right? NAND gates, pretty important for a CPU. And this is your floating point unit, also pretty important, and so on. So you need to place these things, and then you need to connect them using wires. Now wires are of course etched into the board, but you need to connect them according to maybe there's a component right here. According to the netlist, right? They need to be connected like that. So maybe the algorithm that came up with the chip told you they need to be connected like this, and if you lay them out like this, you can draw the wires. So this is your finished. You want to go from the thing on the right to the thing on the left, and your goal here, in order to get the fastest possible computer chip, is three things. First of all, the density is important. By density, it basically just means you can't place stuff on top of other stuff. So you could not place a block right here. Not possible, because the clock is already there, right? So that's first thing, you can't place stuff on top of other stuff. Then the second thing is the wires, and specifically the length of the wires. So you see, for example, this thing here is a pretty short wire. That means the signal travels fast. This thing here is a long wire, so the signal travels more slowly. Now the faster you want your signal to go, that means you have to make your wires as short as possible. So you want to keep the total amount of wire length as short as possible. And then third is what's called congestion. So congestion is when, for example, okay, I actually don't know what it is, but maybe it is when two wires cross, like somewhere here, there might be congestion, or maybe some parts actually share their wires. I can imagine, sorry, I'm going to draw this again. I can imagine maybe there's a part here that wants to go up, and then it maybe shares this part of the wire here with the other one, and so there's congestion, like it's roads or something. In any case, you can measure congestion, and it's a bad thing, and you want to lay out your components basically in order to minimize congestion and also minimize the length of the wires and not have them on top of one another. Easy enough, right? It takes human experts and combined with state-of-the-art algorithms, multiple weeks to design chips like this. And that's the fundamental problem. And this paper takes reinforcement learning in order to solve this problem in a few hours. So how does it do this? The reinforcement learning is basically a sequential method. So you want to do one action at a time. So you start off with what they call the chip canvas, which is just empty. This is your state. And then the agent here, it gets to decide where to place the next thing. Now, how do you decide what the next thing is? I believe they simply go by size. So they take the largest component first of the net list first, and they just go down the net list like this. So you tell the agent, hey agent, I want you to place this thing here. I want you to place this next. And the agent will tell you, I will place it right here. And then again, you tell the agent, I have this thing here. Where do you want to place it? Along with all the connections, right? Along with everything that it needs to be connected to. And also the entire list. So the agent must also think of what is to come yet, what it hasn't placed yet. Right. So everything goes into this decision, and it tells you, okay, I want to place this here. And then at the end, you end up with this filled board. Now, this isn't actually the end. After you have placed all your things, there is another method coming in. This is called this force-directed method, placing yet more things. So what you actually place with this agent is only the things called macros. Now, I have no idea what those are or how these are different from these standard cells, but apparently you must use a force-directed method, which you can think of just an algorithm you run to place the standard cells. And these are these gray blobs here. And at the end of all of this, you can finally evaluate how good your design is. So at the end of this, you get a reward that is a mixture of wire length and congestion. Now, this is actually an approximation to wire length, and this is an approximation to congestion that they use because they need to evaluate it quickly. But essentially, it's highly correlated with wire length and congestion. So the negative of that is going to be your reward. So in terms of a reinforcement learning problem, this is pretty nasty, right? Because, as you can see here, you get basically a reward of 0 for every step until the very end. You get your true reward. And it is actually worse than that because, so from here to here, your agent gets to perform actions, right? This is action time. But usually when you have these sparse reward tasks, you'll get your reward at the end of that action time, but not here. At the end of the action time, there is an algorithm over which the agent basically has no control that comes in and does a bunch of things, this force-directed method, and only then do you get your reward, right? So the agent must purposefully sort of leave room here for what this algorithm is going to do. So it needs to learn that as well. This is as far as reinforcement learning goes, this is a pretty good reinforcement learning problem, right? So now we have an environment, right, which is the canvas here, and also this. You can consider this force-directed method to be part of the environment, and of course the reward giver, and you have also the netlist as part of the environment, and you have the agent that can do actions. Now we have to go into how does the agent perform actions on this. So, by the way, maybe a bit confusing because it was a bit confusing for me. For a given reinforcement learning problem, we'll just start out by saying that the netlist is always the same, right? You might be coming from a deep learning framework where you're used to many different training samples. In this case, basically, the netlist, the goal is always the same. You can think of it like a reinforcement learning agent for the game of chess, where it's always the same chess game that you're trying to optimize. This is the difference to, let's say, supervised learning. If you have a label in supervised learning, if you know the solution to a particular data point, you're happy, right? That data point is no longer interesting. You want to generalize. Here, even though they generalize later, here you can give it a single problem, right? And it will already, a solution to that problem will be valuable because it can be a better solution that humanity has come up with until this point. So always think that we're now just working on one single netlist, one problem to optimally place this netlist. And an episode is simply to place these things until here, and then you get a reward, and then you go back to the beginning and just do it all over again, but just try to do better. And then you go back to the beginning and you do it all over again. The same problem, right? Okay, so how does this work? By the way, the paper has great technical detail on chip engineering and how the reward function exactly works and so on. I have not the expertise to go into this with you beyond what I just described. All right, so here is how the model looks from a deep RL perspective. Now, there's two parts to this model. You can divide it about here. So on the right, you would have what is your policy and value networks, and on the left, the feature embeddings. So in reinforcement learning, and we won't go much into reinforcement learning now, but what you need are basically a way to encode the state. This is the encoder. So all the information of the observation, they might be in different modalities and so on. You need to encode this into, for simplicity, let's say a single vector. That's this thing here. This is the state encoding. And then you can employ a policy and a value network in order to do reinforcement learning. So the side on the right, this comes from standard RL. You have a policy network and a value network, and they do, I believe, PPO with it. This is a standard reinforcement learning architecture. It's an actor-critic architecture. So the value net is simply telling you what's the value of the state that you're in. Now, given that you have a state embedding, it simply takes a fully connected layer to transform this into a single float. That is the value network. The policy is a bit different because usually in reinforcement learning, you just have a list of actions, right? You just say, I have these 16 buttons on my controller, you can press them. Here, if you look at this chip from above, we have a question. Where do you want to place the next thing? So in order to do that, we take this embedding of the state and they run it through a series of deconvolutions. And the deconvolutions, they have the ability to basically upsample an image. So you see here, you transform this vector into a 4x4x32 tensor, and that gets deconvolved into more and more, though less and less channels, but more and more height and width images. So it kind of, from a vector, it produces an image right here. You might recognize this from a lot of generator architectures for when you make GANs for images, have exactly this deconvolution architecture. So, as I said, pretty cool. It pulls in kind of architectures and methods from different fields. We already have reinforcement learning, and now we have generators for images. Now, so you come up with an image, and basically this image, if you can imagine this from above, is discretized. So you can place the thing you have to place pretty much every single nanometer, but they discretize this into a grid. And for each point in the grid, the network outputs a number. So the number may be 9, here a 3, a 4, and so on. An 8 right here. So for each of these, it outputs a number where it would, or how much it would like to place the next thing at this particular location. So this is a distribution over locations. So the first thing you have to do is you have to mask out where there are already things. We said the first condition is things cannot be on top of other things. So maybe you already have placed something here, so you ignore those numbers, and you have already placed something here, so you ignore those numbers as well. This is this masking operation right here. And then you simply look at where is your highest number, and maybe there's an 11 down here somewhere. Say, this is my highest number. Okay, cool. And you look at what you need to place. Maybe the thing you need to place looks like this, and you say, all right, I will place, maybe the 11 marks the top left corner. I will place it right here. Okay, and then you do the same thing again for the next piece. So the next piece, you would simply also mark this to be blue. So you can't place here. You evaluate your network again. Of course, you'll have a new shape, something like this. And then you ask the network, where would you like to place this? And you do this step by step by step until the entire netlist is empty. So this is how we do the reinforcement learning. This is how we decide on an action. But how do we actually put the state into this encoding? Now, this pulls in yet another framework from another field of deep learning, namely graph convolutional neural networks. So since the netlist is a graph, right? The netlist is, again, if you have your, wow, this is slow today. If you have your netlist right here with the part, right, the shape or size, whatever, and the list of things it needs to be connected to, then this forms naturally a graph. So you can transform this into a graph with the things that need to be connected by an edge. And they run a graph convolutional network across that. Now, in a graph convolutional network, you're trying to take a graph like this and have embeddings for the edges and the vertices. So ultimately, you want what's called a graph embedding. In order to do that, you need to propagate information along the graph. Usually, as we said, this is done during a graph convolution. If you are in machine learning for a while longer, you might remember also things like conditional random fields or generally graphical methods that were once popular and are kind of a precursor to this. So the way they do it is they do it in an iterative fashion. They have multiple. So they say this right here. So how do they embed a graph? They have nodes in the graph, as we saw before. I'm going to draw this one again. So this is maybe VI, VJ, and VK. Now these represent the pieces in the netlist that you have to place. So for each of those, it has a bunch of features, right? So the features might be its size, its, I believe they have them somewhere here. Its size, maybe how much power it uses, and also its X and Y coordinates if it is already placed, right? So you start with a vector like this, and then you iteratively do the following thing. You compute edge features by running first these things. So this is VI and VJ. For each edge, you take its nodes, run them through this fully connected layer. So you embed the features of the nodes, you concatenate them, and you run it through another neural network layer. And that's how you get embeddings for edges. And then you update the embeddings for the nodes again by taking the mean embeddings of the edges. So you do this in an iterative fashion. First, you compute the edges from the nodes, and then you compute the nodes from the edges, and so on. Right? So this means that information can now propagate through the graph. So information from this thing propagates into this edge embedding, And then in the next step, that will propagate into this, and then that can propagate into this EJK. And this is the same as if you're used to, something like a conditional random fields. Over time, if you have a big graph like this, the information from any particular node will kind of propagate out throughout the graph. And at some point, you can sort of reach an equilibrium where everyone in the graph knows about everyone else. I have not found how many times they do it. They simply say, we repeatedly perform the following updates. Maybe that's somewhere and I just haven't read it closely enough. But also, I haven't seen whether or not they then backpropagate through these multiple updates, or whether they just backprop through one of them. Not entirely sure. But ultimately, they get embeddings, these edge embeddings, out of this graph, and they simply take the mean to get the graph embeddings, and that goes into their state embeddings, right? Along with that, they also have the macro embeddings, which are the nodes here, the things to be placed, along with the current macro ID. This is which one do you need to place right now. So this comes out of, these are the two things out of graphs, vertices and edges, and then which one you need to place right now. It's pretty important, right? So you take the one that you need to place. This also goes into your embedding, and then you have some metadata about the netlist, like how many things there are and so on. And this is also embedded using a fully connected layer. All of that goes into your embedding. All right, so your embedding will contain all of this information if you've done a good job and if you train it correctly. So this is the model. Now, they do pre-train this encoder part right here. And the encoder part, it's also kind of circular. First of all, they just generate a giant list. So they take this chip here and they just run a policy network that is maybe not super optimal, but they just run it a bunch of times in intermediate states, and they pre-train the encoder to predict the final reward for each of these placements, or sorry, the wire length and congestion and so on. And that pre-trains the encoder. But ultimately, you can train this with reinforcement learning. You can now let it try to solve this board over and over and over and over, and it will get better over time. All right. The last thing they do is they do transfer learning. Now, finding a better architecture for a single board is already better and faster than the humans. But what is cool is that if you have now trained on this one particular board, with one particular netlist, where was it? Right, we've now trained on this particular netlist. This was our problem, and we've solved that. We have a great solution. Can we now, when we get a netlist, another netlist? So here is netlist 2, right? It's maybe a bit different. So this one is more longer, and this one is here, and so on. What if? So we would have to start again from scratch. Train a reinforcement learning agent on the netlist 2. So maybe RL agent trained on chess. If we now wanted to play Go, we'd need to start over again. But they try to just transfer this to the new one. And astonishingly enough, if you train the same RL agent, not only on one netlist, but on a set of netlists, and the biggest set they have is 20. So their data set size is 20. Imagine how small this is compared to supervised learning. But maybe think of this like you train on 20 Atari games, and then it will play the 21st one much better than if you started from scratch. Interestingly though, even zero-shot embeddings tend to be pretty good. So they don't optimize for the new thing at all, and it's already better. You can see that here. So if you train a policy from scratch, then this here, then it takes a long time. But if you fine-tune a pre-trained policy, it's much shorter. And interestingly enough, at the beginning, it is already better than the policy from scratch. That means the knowledge from one chip transfers over to the other chip. So the problems are sufficiently close. And that basically means that if we now want to design a new AI chip, not only are we better because of RL, we're also faster because we can transfer learn. And they show here that this effect basically appears when you have a large enough data set. And again, large here is just 20 blocks. Here you see one of these placements on the left, the zero-shot placement, and on the right, then fine-tuned on that particular architecture. Obviously, me being an expert in chip placement, is clearly obvious that both are extremely good, and yes. Though, actually more funny, I find this one, where they compare human experts to what their approach is, and it says, the figures are intentionally blurred as the designs are proprietary. Like, why do you put them? Like, clearly, I couldn't even judge if they're super crisp. Yeah, all right. I guess it's their trade secret. So they compare this with the standard algorithms for these things, and not only are they faster, they also better on the metrics. Yeah. Overall, as I said, I find this to be a pretty cool work that pulls in a lot of things from a lot of different fields. At one point, they say we propose a novel graph convolutional architecture. I'm not sure that it is novel. Maybe it's novel for this problem, but I'm pretty sure graph convolutional networks and things like this have been around for a while. But again, it pulls together things from many different fields and applies them very well engineered paper, and a step towards the singularity, as now AI can design AI accelerators. How amazing. Yeah, humanity is doomed. All right, I invite you to check out this paper if you're still here. Please subscribe, leave a like and a comment, and I'll see you next time. Bye-bye.